Hello and welcome back to the development of the Feersum scheme compiler. So in the last stream we looked at implementing parsing for a few extra comment types. So in scheme you can do a standard single line comment using a semicolon, and we added support for block comments and datum comments. So let's start by going over what we did last time, and then we can discuss what we're going to do in this stream. Do shout out in the chat, by the way, if you've got any comments. So we worked in the syntax part of our compiler last time. So syntax is our parser, and we worked on this comment parser. So the comment parser is used whenever we're expecting whitespace or comments to recognize the different comment forms that we support in our scheme. So previously we used to just recognize this form, which is a single line comment, which is a semicolon, and then because these parsers don't produce any output, we use skip to skip the rest of the line. The first extra comment type that we added was datum comments. So if you see a hash and then a semicolon, instead of commenting out to the rest of the line, we use parse form and then skip it. And in the block comment case, we needed to create a parser ref beforehand, because block comments are actually recursive, because a block comment could contain another nested block comment and so on and so forth. And the way the scheme works is that if you comment out some code that's got a block comment in it, the inner block comments are counted correctly, so that you don't end up with your block comment becoming accidentally shorter than you intended it to be. Okay, so that all allowed us to parse some extra comment types. So here's an example of a block comment, and I can put a nested block comment in there too. So yeah, well, the syntax highlighting shows it works, but the compiler would also be happy with that. I'm going to back that out because it's going to cause the unit test to fail if I don't. And we also recognize datum comments. So in this case, this is not commenting out the rest of the line, it's actually commenting out this specific datum. So if I was to do it like that, even though the syntax highlighting in Visual Studio Code is not telling me that, this would actually still produce the same parse tree, because the comment is commenting out the whole form. So just to prove that, actually, let's run the test and check that it is actually working. It must have worked because we haven't got any errors. So go to tests, see the test output. It's going to be in the terminal in the test task. Yep, all the tests still passed, which means that the parse tree for this, even though I've edited the source code, it still parses to the same thing. I'm just going to back that out as well. Right, but writing this test case, last time we ended up with a few corner cases that are down to not implementing scopes properly and not having support for built-in functions. So the first problem we had is that fact can't call itself recursively properly, because when you call define fact, it's defined out here in the global scope, and then in the body of the lambda we're considering that a different scope, and we don't yet support inheritance of scopes properly. So like when you look at a variable up here inside this lambda, if in this case n, we look it up in the body of the lambda, but we don't look it up outside. So that's something that we need to do at some point, but I'm not sure we're going to tackle that today. And the other one is that there's several identifiers that you would expect to be bound to things in a normal scheme program. So you expect like plus, minus, times, divide, and that kind of thing to already be there, so that you don't have to redefine them. So that's what we're going to look at tackling today. So the first place that we need to go to deal with this is we want to define a default scope that contains the method, the extra symbols that we're going to introduce. So we're going to go to the compiler, maybe? I'm trying to remember now where I actually put the base scope. Well, we'll have reference to it in the evaluator. So the evaluator starts off by creating, compiling into in-memory assembly, right? So yeah, create root scope. So in create root scope, at the moment, we start off with an empty map. So what we can do is we can start off if we start off with all of the elements, it's map from seek to map, isn't it? Nope. How do you create a map with default values in it in F#? F# collection initializer. Map of seek. So what was the type of the type? It's just a generic map, but we use it in the compiler. I'll use it in the binder when we create the bind. So we give it a scope. So it needs to be a string to storage ref. So we will create a list which contains all of our built-ins. So at the moment, let's just have a single built-in of plus, and we can do this. I think we can do this like as a pair. So it's going to have a plus, and we can do a symbol, a storage ref. Well, at the moment we've only got arguments, globals, and locals. So we'll pretend it's a global, and we will have to add a new type of storage for this. This value is not a function. cannot be applied. Okay. A map of strings. Ah, yes, because global needs to take a name. I'll give it the name plus. Right, there's too many closing brackets there. That at least compiles now. Right, so the idea is that we will adjust this root scope so that we've got some symbols in there already. So the first thing we need to do is come up with a new type of storage to represent these built-ins. So I'm just going to call them built-ins, and we can refer to them by string. Then where we create that, where we create the root scope, we can use built-in. And I'm going to simplify this a little bit more because we can turn this, we can use a map to change that. We can do a seek.map because we don't actually want to build another list, and we will map it from S being symbol, and we will take the symbol and we'll return a pair of the symbol and storage ref built-in of that symbol. Good. So the idea is that we can now add other symbols in here. So we'll just do plus, minus, times and divide for the time being. So that change on its own should be enough to allow us to start binding programs that have got references to one of these, but we won't be able to actually compile anything for them yet. So there should, yeah, so what's going to happen is when we actually try and define something, or when we try and load something, we will fail. So if someone tries to define a symbol and it is a built-in, we will raise an error. Can't redefine built-in, and we'll just use its name. Okay, then definition, if we have a load from a built-in, we need to decide what to do. But that should be enough to be able to start actually binding programs that contain references. There's 2 warnings, but they're both from the interpreter, so I don't care. Just to be clear, there's an old tree walking interpreter in this compiler, which is now being replaced by a more modern interpreter, which instead of walking through the tree and building up values and stuff in memory and that kind of thing, what we do is we take the source code, compile it into an in-memory assembly, and then use reflection to call the body of the script rather than interpreting it. So I'm planning on getting rid of the old interpreter for a while. So if I do something like this, we should get to do implement load from built-ins. So this program was parsed correctly, and when we tried to bind it, we bound it as an application of loading from the built-in plus, and then these 2 as the arguments. But when we came to actually try and lower the load, try and actually do some IL emit for it, we failed. So before we can actually load those built-in values from anywhere, we actually need to emit them. So in our emit context, where as we travel around, we've got our assembly, we've got the IL for our current lambda or whatever that we're loading, we've got a bit of mutable state to keep track of what the name of the next lambda that someone defines is going to be. We've got the current scope so that we know where to define lambdas so that they don't clash. We've got access to the root program type, and we've got access to the cons type so that we can create cons lists. So we need somewhere where we can store all of these built-ins. So in the future, what I would like to happen is that the built-ins would be in another .NET assembly, and that assembly would be referenced, and the calls would basically just be standard .NET calls out to the implementations in that assembly. Probably use attributes or something, and some, well, I was going to say reflection to work out where we want like inspect a given assembly, and anything that's got the built-in attribute or something on it is exposed to scheme as a built-in with some nominal name. But could also have a look at using source generators or something like that to make that nicer so that we don't have to do reflection. But for the time being, we've only got 4 built-ins so far that we want to support. So the pragmatic decision here is to put those built-ins somewhere that we can already access them. So instead of referencing a pre-compiled assembly like you would do in a normal compiler, in a full-scale compiler, the F# compiler has f#.dll or something, which contains all of the built-in bits of code that the compiler relies on to make your program work. Same thing for the C# compiler. We will have to get an assembly like that in the future, but for the time being, we will just re-emit them into the assembly that we're building. I am tempted to just put them on the program type for the time being. So if someone has a reference to a built-in, we will just look it up as a static field on the program type. And that does mean that they alias the globals think we should be okay. So what we need is we need a way to get access to the field definition so that we can do the load. So I think we might want a map here. Should we just call it built-ins? And it will be a map of string, which is going to be the built-in ID, to field definition, which is going to be the field probably on the program type. So then when we actually want to reference it, to load it, we can do something like let field equals context.fields are built-ins. ID, and then we can do, what's gone wrong there? Yeah, maybe we should don't know if we actually want to handle the case where we can't look the built-in up, because that's more of an error in the compiler. Like, we failed to write the compiler correctly because we've somehow bound something that we didn't have a built-in for. So I'm just going to let it fail catastrophically in that case. So it can't work out an overload for emit, and that is because I did the indexer wrong. Right. So if we have built-ins, we will now be able to load them. But when we create the root emit context, we're not creating any of these built-ins yet. So we already have add core decals. I think we're going to have another method which returns the built-in types, and we'll use that to create our built-ins. It's going to need access to the program type, and probably it's going to want access to the assembly as well. So let's do create built-ins. We take an assembly and we take a program, we can just call it type, and we return a map. We can just return an empty map for the time being. I've spelled built-ins wrong. That rename's not worked. I'm going to go and try and rename it from the field declaration. Sorry, record declaration. No, let's just use find and replace instead then. Right. So create built-ins should, if we try and run this now, it would fail because we don't have a built-in. We haven't added a built-in to the program type. And so let's do the same thing. Just call plus. And we should get given key was not present in the dictionary. Good. So everything's working. Now what we need to do is actually make that dictionary contain all of the types that we need. So we'll start off by defining a method. So let's take the declaration of the main method. So for example, for the plus, it's going to be public and static, and it returns an object. Why is this not working? Object of indeterminate type. This is because I need to annotate this and tell it it is an assembly definition. Good. And I need to tell it this is a class definition, I think. Type definition, yeah. And then we need to actually build the body of the plus method. So plus, I'll do IL is going to be, yeah, plus dot get IL processor. And so we want this method to be called with an array. So let's see. So yeah, we do array type object. And this is going to be, yeah, object here. So we take an array of objects and we return an object. So this is matching the calling convention of our unified calling convention for lambdas, and that is not a coincidence. So the plan here is that the plus method will, when we will lower the method, and then we will we'll create a field that basically just contains a func or a delegate that just wraps that method. So from the caller's point of view, you wouldn't be able to tell the difference between it and a lambda that we've emitted. So we've got our parameter, and then we'll just call that args or something. Then if someone calls plus, the first thing we want to do is the plus body is effectively going to be a big loop where we start off with IL.emit, so we'll emit an opcode for load 0, and then what we'll do is we'll just loop through the array and add that onto the accumulator effectively. So there's actually a special opcode just for loading 0. We use that. Then what we want to do is I think we might need a local variable here to keep track of how far through the array we are. Just trying to think of a way that we can work our way through the array without doing that. We've either got to store the accumulator in a local, or we've got to store the index in a local. So we will do plus so we want the accumulator to be sorry, not the accumulator, this is going to be the index, so we can just make it an int 32, and people aren't going to be using that many. That can just be variable definition like that. We need to remember to add that to the body, so plus start body variables dot add. I think there's an overload of this that takes a no. I thought there was an overload that took a name, but if not, so we've got our variable. So the first thing we want to do is set that to 0. So We will emit a duplicate and store that back. Store local in I. So we've got 0 on the stack and we've got 0 stored in our index. What we need to do is, I think we might also benefit from so first thing we need to do is check to see if I is greater than or equal to the length. So we will load. First thing we'll do is so first thing we have to do is load the arguments array, which is load arg0, because this is a static method. So the first of our parameters is at index 0. Then we do load len on that to load the length. Then we do we load the local I, then we do branch if less than or equal. I think we want to do, so which way do we want to do this? I think we want to say, I think we want this branch to be true if we want to continue adding. So I think we want to say branch if less than or yes. So branch if less than, and what we'll do is we'll branch to the loop. So first we'll create an opcode. So we create an opcode and then emit it manually. Then we can use that to jump back to the top of the loop. The other thing we're going to do here at the top of the loop is we're going to emit a jump. We'll create these two labels. We'll create a condition. And we already know that the condition is going to be load arg0. And then instead of doing emit down here, we can do append cond. So the first thing we'll do is branch to the condition. So what we'll do is we'll start off with our default stack state, jump into the condition, and then we'll evaluate the condition and jump back up to the main body of the loop if the condition passes. And then we'll keep on going through until eventually we'll fall out the bottom. So we'll fall out the bottom if this branch if less than fails. So that means that we've reached the end of our array. And then we just want to return. So at this point, we've got, when we jump into the condition, this loads two things. Does the branch of less than, so that should leave the stack set with just the 0 on the top. So what we need to do is load the argument out of the arguments array, we'll load arg0. We then load element ref, because we know that the element in the arguments array is going to be an object. So now at the top of the stack we've got our integer, and on top of that we should have an object. So what we need to do is unbox that object and check that it's actually this doesn't want to be an integer, this wants to be this wants to be a real. Because all of our numbers in the schema implementation at the moment are represented as inexact reals, just for simplicity. So we would do an unbox, and what's unbox any? I'm just going to look up what. Converts the boxed representation of a type specified in the instruction to its unboxed form. An object reference object is pushed onto the stack. An object reference is popped from the stack and unboxed to the type specified in the instruction. The resulting object is reference or value type is pushed back onto the stack. Unbox followed by load obj. Okay, unbox any is what we want because we're dealing with value types here. And then we need to give it the type, which is going to be, that wants to be double. So we load it, and then we want to add. So the value at the top of the stack should then be those two values added together. Right, I'm going to just hugely optimistically try and run that. So if we do +1, 2, we'd expect 3, but probably going to get some form of error along the way. Oh, we will get an error because we haven't actually stored that in a field yet. So we've got the plus method definition. What we want to do is we want to create a field definition . Trying to work out, do we want to have to create a field for every single one of these? Or what we could also do is when someone references a built-in, which I think is what I'm going to do. I think this is the way we should go. So if we have like plus and we add all of the other built-ins in later, and we do so we have like plus, it's the plus, and we do map from seek of seek. So in our map we have the method definitions. We'll change built-ins to be a map of method definitions, and then that should cause there to be an error somewhere further down, where we actually try and load that method. So we get the, yeah, so I don't know, maybe that works. Maybe you can load a method as a field and it'll just work. I have a feeling what's going to happen is that the .NET runtime is going to complain and tell us that we need to turn it into some kind of closure or whatever by wrapping it in a func. So what exception did we get? We got argument exception opcode, because ILEmit can't use load static fields on field when, sorry, the one above, when it's a method. So we want to do load, it's not an element, not a field, not an index, not a local, not an arg. Load virtual function. Does that imply the existence of a load function? Yes. So if we load the method, then what we want to do is box it up in the same way that we box up the thunks that we generate for the lambdas. So let's go find out where that is. In emit name lambda, we create the thunk. Oh no, I think it was just where I was looking. So we call emit named lambda, Then we create a func. So we load null, load the function as a method reference. We'll call a new object. So I think this wants to be extracted into some kind of local, some kind of method. I don't think there's anything in there that's particularly complex. We need to pass in the context to emit because it's referencing func object and all the rest of that. But emit method to func context method, and then up at the top we can have a method that does that. Because it can't work out that that is going to be a method method reference. Good. Sequence. Good. Then when we call emit built-ins, we load the function in fact it did the load function as well, didn't it? So we get the method and then method to func context and math. Maybe that works. I mean, I'm pretty hopeful about this because the lambdas are effectively the same as these built-ins in terms of that they are just methods on the program type. Whether or not that actually works, I don't know. Common language runtime detected an invalid program. Script body plus object array. Good. Searching the wrong place. So plus, what does it do? Well, let's get rid of all of that looping and then see if it's still an invalid program. This is a kind of recurring theme. I initially write out the whole body of the function in IL, adamant that it's going to work, and then reality hits and the .NET runtime's all like, oh, the method, that's not a method, what do you think that is? So now we'd expect plus with any amount of arguments to not do that. Oh, I know what the problem is here. We have not boxed our integer. We want to box it. And do we need to give box any arguments? We do need to tell it what type that we're boxing. Good. So there's a box somewhere down here, which I think is probably us. Yeah. So I have a feeling what happened there is that we basically return null and then try to use it. Or not even null because it was a float. Okay, so we're getting 0 if we try and use plus, no matter how many things. Good. Let's see whether or not the loop I wrote earlier still works. So we have a branch to the condition. Load or I branch if less than, that is not. It's not going to terminate that loop because now we're actually decrement the index, but I'm confident enough in my ability to press Ctrl C that we'll see whether or not that works. No. Load arg. So we need to load the object array, load the index. This is where we need to then duplicate the index and store it back. So we need to load constant I for 1 sub to take it away. So we load the object array, we load the index, take a copy, decrement it, store it back. So then we're left with the original index on the stack, which is the one that we checked in the condition. Then we load element ref, then we unbox. Come on, compiler. Still an invalid program. Is there a special version of add or something? What's OVF? Wonder if that could be it. That's about overflow checking. Add says adds two values and pushes the result onto the evaluation stack. Integer addition wraps. Floating point overflow returns positive infinity, which kind of implies that you can do floating point add with add. So instead of load element, how about we just pop it? The other question is, have we got load element ref the right way around? It seems to be load arg0, load constant for the index, and then load element ref. So I wants to be an integer because the index is an integer. Could that be it? Could this be the source of our invalid program? Nope. Let's get rid of this loop completely again and just check that this is actually working. So let's put some nominal value. As the default and check that we actually get that, because I'm not 100% sure that the 0 that we were getting first was actually a real 0 or that we were accidentally reading from address 0. Right. So let's try and add the looping in. So we've got the condition, the loop, and let's have this loop do nothing. So this loop's going to load I, not duplicate it, load 1, subtract it, store it back. So you'd expect that to still return the same dummy value, but just take a little bit longer about the whole thing because it's going to loop around a bit. It did. So if we load argument 0, then load the index, duplicate it, load a constant, then the sub should mean that we're left with just one value on the stack, and then we store that, so that should clear off this piece of stack. We should be left with load arg, load local. And then if we do a load element ref and a pop, it should load the object out of the array and then discard it. So again, we should still get our nominal value, but it should take a little bit longer because we're looping around. It's not happy about that. Detected an invalid program. What I'm thinking is that we know that the load local I, this part here, which is doing the decrement, we know that this bit worked. So I'll move this to behind the condition. And then we've only got to worry about making this little bit here balance the stack. And then that does look an awful lot like load element ref. in other places. Load constant I4. Load local I. I'm wondering if my stack balancing was bad before and I ended up without the 2 doubles at the bottom of the stack for some reason. No. Index was outside the bounds of the array. Because the indices are supposed to go up. You start off at 0 and add to work through an array. Fair enough. I mean, it's this kind of professional level of programming that I'm known for. When things go wrong, it's usually because of something either incredibly complex or incredibly simple. Often, when you think it's something incredibly complex, it's actually something incredibly simple. You just don't know why it's simple. Index was outside the bounds of the array. Okay. This wants to be like that, I think, because you want I to be less than the length. Which is awkward because condition is one of these labels. So what I'm going to do is just going to make condition not for the time being. We can tweak that later. And then we can make, let's get a load arg. So we will load I, load the length. There's going to be I is less than the length of arg0 as our condition. So if I start off at 0, the length is 0, we don't loop. If the length is 1, we do loop. Read from index 0. Increment I to 1, then you should fail. You still get that. So instead of just popping, how about try and unbox the value into a double? What happens if you try and unbox something that isn't of that type? Did I restart that? We're not going through the loop, are we? So we branch to the condition. Load I, load 0. Branch if less than up to the loop. I can't see why that's not going to go through the loop. There must be something that's broken here. One, two, three, four. That's still our nominal value. So let's change that to 0. Just checking what the unbox opcode does. So we've got unbox any there. Value type has two separate representations. A raw form when the value type is embedded within another object. Or a box form when the data type is wrapped. The unbox function converts the object, the boxed representation of a value type, to a value type pointer unbox does not make a copy. The object is not a value type. Fair enough. So this basically converts the object reference into a pointer to the actual boxed value. Whereas unboxed any does that. And then calls load obj to actually load the value. Index was outside the bounds of the array. Interesting. comparing the wrong thing somehow or other. If I is less than the length of 0, we branch up to loop. It just tells you what the upgrade is, so that's not very used to anyone. BR is just a standard branch, right? Yeah, unconditional branch. To the condition, so we this duplicate instruction up here was meaning that our initial value was being duplicated, and what we actually want to do is load 0 as an integer to be the base of our stack, and load I for 0. So basically load 0 as a real, as a double, to be the initial value for the calculation, and load 0 as an integer to use for I. Still not 100% sure I've got the condition the right way around down here for the way we branch around the loop, but we'll find out. 0. The condition's the wrong way around. So, what is the representation of 00? Public. It is all zeros. But we try to use it as a 4 element. So I was just inspecting in SharpLab what the float value that we were using was. God knows what the 1, 2, 3, 4 float value was. $21. So plus on its own. So I expect this to be 0. It is. And if you just apply it to a single number, you should get that number back. I mean, close enough. Right, so I'm happy with that implementation of plus for the time being. What we need to do now is effectively duplicate that and do a whole load of built-ins for all of the different methods that we want. So I think the first thing to do would be to we've got all of this IL and various other stuff. So what I want is plus to be whole block, and then create the method to indent the whole lot. The idea here being that if we make a method then we can call it and we need to I think that's expecting the unit value there like that. And then all of these bits of IL and variables and that kind of stuff are all inside the method here. And then we can have a create minus and that kind of thing. But I'm going to take a break and come back with... That's not worked. Why has that not worked? Create plus returns unit because we don't return it at the end. Here you go. Go back a bit. So we've got the plus method working, but we don't have any implementation for the minus method. So I'm going to rename create plus to create arithmetic built-in or something, because I'm hoping that the name of the method and the opcode to use to combine them will be enough to be able to abstract over some of these. So if we say name, then we can rename this to be method. Let's just go math again. What else do we reference plus? So we've got a variable for our loop. So our loop's good. We don't need to be doing anything with that. This opcode here, where we're actually combining the values down, we will change that to an opcode. So now we should be able to call, instead of calling create plus, we should be able to call create built-in with plus and opcodes.add. And if that all went well, we should also be able to call, actually let's do it this way around, with a semicolon at the beginning. We should also be able to call minus with opcodes.sub. So let's just give that a test. So these numeric built-ins in Scheme are quite interesting in that they can accept any number of arguments, even 0 arguments. But it gets a bit more interesting when you consider what happens when you're dealing with division and multiplication. So let's see, does plus still work? We're expecting 24, we get 24. Plus with a single value still works. How about minus? That doesn't work because we would expect minus to start off with the initial value. So we can change our loop a little bit here and say if because you'd want like minus 2 is what we'd expect, and the same as like plus 2 is what we'd expect, and we can get to both of those values by adding them, taking them away from 0, which is our default value. But for plus 1, 2, we get what we expect, but we could get there by starting with the 1 and then adding. For the minus, we need to start off with the 1 and then take the 2 away. So in both these, we could do the same order of operations. It's just going to be a bit more complex for the plus case, but it doesn't matter. So what we want to do is, before we do the main loop, we start off with I at 0. What we want to do is check to see if the length is greater than 1. So we'll get the length, and if the so we're saying we loop back down if I is less than here. So if the length is greater than one, two, so where do we want to go? I'm thinking if it's greater than 1, like if we've got enough to be able to load the initial value and then do something else with it. We want to do a bunch of code and then jump to the condition. Otherwise, we just want to jump to the condition. So I think we move our condition opcode higher up and say if we have fewer than or less than or equal to 1, then we'll go to the condition, because we know that's going to do the right thing for the single case. And then if we've got more than 1, what we will do is load arg0, load element ref, unbox any. So we basically pop, what we want to do is pop the starting to get complex here. We create another label. We can basically start off with our load arg load length. If we have a small number, we will branch to setup. So in setup, we will do that bunch of stuff that we used to do, where we load 0, load as a real load the index, set the index to 0, and then we start and we jump to the condition. If we're not doing the setup, well, first thing we need to do, we load arg. If we're not doing the setup, we're going to load arg0, load constant 0, load the element at index 0 and unbox it. So that's the equivalent of loading the default value onto the stack. Then we're going to load 1 because we want to start our loop at 1 and then branch to the condition. So effectively, if we've got a simple setup, we just do this. If we've got a complex one, we load the first element out of the array and start from there. So this way, we don't like push 0 onto the stack first for adding, but we also don't push 0 onto the stack for subtracting. Does +1, 2 work? It does. +1 crashes. Why? So let's try and see whether or not it works with a minus. So let's do 5 minus 2, so it should be 3. It is. Minus 2 is minus 2. Minus on its own is 0. It's probably going to be negative 0 technically. Plus on its own is 0. Plus and a 1. That works. Confused. Looks like it works. Then, to be able to deal with division and multiplication, we're going to need another parameter in our arithmetic operation. So if we start off, if we do multiply starting off with 0, this is going to return the right thing as long as we've got more than one argument. But you'd expect that if you do multiply and then only provide it a single argument, you get that same thing back. So 1 times 2 should be because I'm still using the div and mul. good. It's always something complex or something simple. It's one of those things that sounds like it's deep, but it's really not. Because surely everything is either simple or complex. Two. 20. But what happens if you do times and then 3? It's going to be 0 because it's going to do 0 times 3. Really, you'd want that to be 3. And what about, like, if I do divide 1 by 2, you get 0.5. What if I do divide 3? Doing 0 divided by 3. So we also want to be able to parameterize the default value. So the default for these arithmetic ones was 0. In these cases, it's going to be 1. And then where we do, we can't use the word default. Where we do 0 to 0, we do default. And it doesn't know that that is a double. Should be 0.5, and if I times something, we end up with the same thing back. So now we should be able to do something like 3 times 4 plus 5 divided by 2. Yes, that is correct. Right, so let's review what has changed and stage it. So in the binder, we've got a new built-in type for storage reference, and in the root scope, we have the plus, minus, times, and divide. And then in the compiler, we have a built-ins set, which is a map of methods. When we are lowering references to built-ins, we explicitly say that you can't redefine a built-in. And we handle the case where you try and reference a built-in by taking the method out of our built-ins table and then emitting a system.func reference to that method, so it looks as if it was a lambda or anything normally callable. We've extracted out the emit method, so we could use it in the lowering of the built-ins. And then we've got this create built-ins method, which most of the work is done by this create arith built-in, which creates a loop that goes over the arguments it's given and does some arithmetic with an operator. And we've defined a set of those for plus, minus, divide, and times, because I've done them in a slightly different order. And we actually initialize the built-ins when we create the first emit context. That's it. What is it complaining about? Oh no, it's just references. So there is also the problem of the interpreter to fix up. So the interpreter just want to add in a couple of fails. So when you try and store, we complain about it. When you try and load, we complain about it. So that's it. Thanks for watching, and I will see you next time for some more work on the Feersum scheme compiler. So now we've got built-ins for arithmetic operations. I'll probably add some built-ins for the display function, which just prints out what it's given, and then we can have a look at solving some of the other scoping issues that we saw at the end of the last stream to do with not being able to look up values in outer scopes. Thanks for watching.